In this module, we're going to look at another kind of design element called an accumulator. And there are three basic ways to use accumulators. Rather than explain them up front, though, what we've done is to break the videos this week into three sections. The first kind of accumulator we're going to look at is something called a context-preserving accumulator. And we'll see that what this does is it preserves context that otherwise gets lost in structural recursion. Now, when you design with an accumulator, sometimes you realize up front that you're going to need an accumulator, and sometimes you only realize partway through the process of designing a function that you will need an accumulator. So in this first example, I'm going to pretend that I don't yet know I'm going to need an accumulator, and just start designing it without an accumulator, and that'll help you understand, I think, a bit better the exact problem that the accumulator solves. So I'm in skip1starter.racket, and the problem is to design a function that consumes a list of elements and produces the list consisting of only the first, third, fifth element. So it's basically going to skip every other element. So let's get going. It starts out as a normal how to design functions problem. Let's see, we're going to consume list of, and it says list of elements. It doesn't say what the elements will be, so I'll just say list of x, and then produce list of x. So this function, at least according to its signature, should work on any kind of element. Produce list consisting of only the first, third, fifth elements of blocks. Here's the stub. We'll call it skip1 because that's what the problem asked me to call it. Now let's do some examples. Well, whenever you're given an example for free, you should use it. So we'll start with this one. And we'll do another one. Let's see, we'll copy all of this just to save typing. And let's see, this time, let's just use numbers, what the heck. 1, 2, 3, 4, 5, 6, and we're keeping every other one. In some sense, if we number the positions starting at 1, we're keeping the odd numbered positions. So let's see, we're going to keep 1, 3, and 5. Okay, there we go. Okay, there we go. Let's run these examples to make sure they're well formed. They are, the tests fail. Great. This is a function operating on list of x, so let's template it according to list of x. It's conned empty LOX is something, and this is just the usual list of template, which by now you know by heart. And you might have thought to put fun for x there, because we don't know whether x is going to be a primitive type or a programmer-defined type. But because this function is going to operate on any x, that means it's probably not going to do much with that x, or it's certainly not going to do anything that's particular to x being a certain type. So I'm going to just leave this out, because I'm sort of saying I'm probably not going to need this. You could have put it in and then you edit it out later, remember. Templates are the skeleton. So let's see, there's the template. And we didn't make a specific case for empty, but we could do that now if we wanted to. If you skip one of empty, what do you get back? Well, you get back empty. And so I'm going to put empty there. And this function is really doing a kind of filtering thing, right? Sometimes it keeps the first element, sometimes it doesn't. Let's see. If sometimes it keeps the first element, then we'll cons first of blocks onto the skip. Sometimes it doesn't keep the first element, we'll just do the skip of the rest. Now the question is, what's the test here? When do I keep the first element? When don't I keep the first element? Well, I kind of said it here. This example is making it a bit clear to me. I keep the first element if there happens to be a predicate called odd, if what? if the position of first LOX is odd. In other words, I need to know, when I'm doing A, because its position is odd, I'm going to keep it. But when I'm here, because B's position is even, I'm not going to keep it. When I get to C, because its position is odd, I will keep it. But position, I don't know what the position is. In some sense, at the beginning, I maybe know that the position is 1. But by the time I get to the next element and the next element and the next element, I don't know the position anymore. What's happening is that this information, this context information about how far down the list I've marched, is lost by the template for structural recursion. The template for structural recursion gives me each element of the list beautifully. It gives me the natural recursion beautifully. It allows me to work with those beautifully. But what it loses is any knowledge of how far down this list we've gone. Now, this is one example of the kind of problem a context-preserving accumulator is going to solve. It's going to preserve for me the context of how far down the list we've gone. So that's the setup for the problem. And in the next video, we'll start working on the solution.